Okay, so in the last video we talked about the concept of net force. And remember, when we talk about net force, we're talking about the sum of all the forces acting on that object. Okay, and so what you're adding though are vectors, because force is a vector, and so it's a little more complicated than just adding up numbers. And we did some examples in the last video where we saw that really when we talk about net force, you can think about the net force as being a vector where, let me just write this down, where you have an F net x and you have an F net y. And so F net x would be the sum of the forces in the y direction, and F net y would be the sum of the forces in the y direction. Actually, let me say that again. F net x is the sum of the x forces, so F net x, and F net y is the sum of the y forces. And so when we talk about the net force, we're talking about adding those forces up. Okay. Now, today we're going to talk about Newton's second law, and so you'll see where the connection between net force comes into what we've been talking about. So let's talk about Newton's second law. Now, Newton's second law is probably the most important equation we're going to see in all of mechanics. Okay, and so here it is. F net equals ma. The net force on an object is equal to the object's mass times its acceleration. Okay, so this right here is Newton's second law. F net equals ma. Okay, and this is an incredibly important law in physics and engineering. Basically what this law says is, if you look at the left side is the sum of the forces acting on an object. And the right side has to do with mass and acceleration, which we know what acceleration is from the last couple units. Acceleration is the rate at which your velocity changes over time. And so this is the law that connects dynamics to kinematics. On the left side, you have all the different pushes and pulls acting on an object all kind of combined together, and on the right side you have mass and acceleration. In other words, if you can somehow write down what different pushes and pulls are acting on an object, then you can describe how that object will accelerate. And if you know the acceleration, then you can also figure out the velocity and the displacement of that object. Okay, so this is the connection between force and kinematics. Okay, so I call this equation the killer bunny equation, and the reason I call it the killer bunny equation is because it looks very cute and simple. It looks like a simple thing. There's only three things in the equation: net force, mass, and acceleration. But actually doing problems with this equation is much more complicated than it seems. And so if you don't know what I mean by killer bunny equation, I will link a video clip that I like to show every year with a killer bunny in it. And that's just, again, for fun. It's just a fun name. And the reason, again, is because even though it looks like a very simple equation, actually doing calculations with the second law, as we'll see over the next couple of months, because we'll be doing second law problems over the next couple of months, actually doing problems with this equation can be quite complex. Okay, so let's talk about how you solve problems with Newton's second law. Now, again, because we're going to be doing second law problems for the next couple of months, it's really important that you take good notes here, because all the problems we're going to see from now until, let's say, the end of, at least the end of the semester, if not longer, follow the same basic process. Okay, so it's really important that you add this to your notes. So here's basically how to apply Newton's second law. Step 1, draw a free body diagram for this situation. Step 2, determine whether or not the object is accelerating. Okay, so F net equals ma, so basically this is saying to figure out the right side of the equation first. If the object is accelerating, then the acceleration is not equal to 0. Sometimes you'll be given the acceleration, sometimes you won't. If the object is not accelerating, then the acceleration is 0. Okay, and you know it's not accelerating if the object is at rest or if it's moving with a constant velocity. Step 3. Once you figure out the right side of the equation, you figure out the left side. Determine the left side of the equation, okay, the net force. So remember, net force is equal to mass times acceleration, but net force also has its own definition, because that is the sum of the forces acting on an object. This means writing out the sum of the forces acting on the object on the left side of this equation. Okay, you should write out the sum of the forces before you plug in numbers. I promise if you do that, it'll make solving problems way, way easier. When you do write out the sum of the forces, when you do go to plug in numbers, do make sure that you take into account the direction, because what you're adding on the left side is you're adding up vectors. Okay, so the direction is important. Okay, so we're going to start off with some simple examples in this video, and then over the next few months we will increase our complexity of problems that we solve with Newton's second law. Okay, so make sure you have this added to your notes, and we'll start off with some very basic problems. Okay, example 1. A ball is taken to space, which means we can basically ignore the force of gravity, and is pushed by two different forces. One force has a magnitude of 10 newtons and is directed to the left. The second force has a magnitude of 15 newtons and is directed to the right. Assuming the ball has a mass of 2.5 kilograms, calculate the acceleration of the ball. Okay, so just really quickly, I'm going to figure out I've got the mass, I'm looking for acceleration. Step 1 in any second law problem is to draw a free body diagram. So we have a force going to the left. I'm going to call this F1. And then we have a force going to the right. I'm going to call this F2. Notice that I've drawn the arrow to the right longer than the arrow to the left, because I can tell from the problem that the force to the right is bigger than the force to the left. 15 is bigger than 10. Okay, so step 1, draw an FBD. Step 2, determine if the object is accelerating or not. So I'm going to start with my second law equation. F net equals ma. Specifically here, because these forces are horizontal, I guess I should say this is F net x, and this is ma x. But step 2 basically says to figure out whether or not the object is accelerating. Now we don't actually know what the acceleration is, we don't know the value, but we do know that this object is accelerating, just because we can clearly see from the FBD that we have a net force to the right. Therefore, this object is accelerating. So I'm going to fill in what I do know for the right side. I know the mass is 2.5. I don't know the acceleration, so I leave that in there. And then we go to step 3. And step 3 says, write down the sum of the forces. Always make sure you write down the sum of the forces before you plug in values. And you might think, why is he saying to do that? It's such an easy problem. But as we go on to more difficult problems, writing out the forces before you plug in any numbers is going to make solving those problems a lot easier. So what I'm going to write down on the left side is I'm going to write F1 plus F2. When I say write down the sum of the forces without plugging in numbers, that's what I mean. Okay, so I'm done with the 3 steps. Now I can actually plug in numbers and try to solve. I know that F1 has a magnitude of 10 newtons, but it's also directed to the left in the negative x direction. So I'm going to plug in negative 10. For F2, I have 15 newtons to the right, so I'm going to do plus 15. On the left side, negative 10 plus 15 is 5. And to get AX by itself, I divide both sides by 2.5. By the way, this is exactly what your work should look like for these problems. So this is the answer to the question. Okay, the question asked me to find the acceleration of the ball. I found the acceleration of the ball. Okay, I started with the free body diagram. I went to step 2, which is to deal with the right side of the equation first. I figured out that yes, it is accelerating. I don't know what the acceleration was, so I just wrote AX. And then I went to step 3, which is to write out the sum of the forces, and then I plugged in numbers and solved. Okay, so this is a second law problem. Okay, pause there if you need to finish looking at that. Okay, let's do another basic problem. Okay, example 1.5. It says, using Newton's second law, calculate the acceleration of the object shown to the right. Now here we actually have a two-dimensional problem. You can see from the free body diagram we actually have forces in the x direction and in the y direction. And don't forget when you see that because the approach is the exact same, we just have to go through the process twice. Okay, so step 1 would be to draw a free body diagram, but we don't have to do that because 1 has been given to us. So step 2 is to determine if the object is accelerating or not. In other words, deal with the right side of the equation first. Now what I'm going to do is I'm going to write out my second law equations, but I'm going to do it twice. And the reason I'm doing it twice is because I'm doing it once for the x forces and once for the y forces. When I say ax, I mean the x component of acceleration, and when I say ay, I mean the y component of acceleration. Now steps 2 says to figure out whether or not the object is accelerating, but we need to do that in both the x and y directions separately. So let's look at this FBD. I see that for the x forces, I have 15 newtons to the right, I have 45 newtons to the left, and so I know right away that because the forces are not balanced in the x direction, this object is going to accelerate in the x direction. Now, do I know what the acceleration is? No, but I know it's not equal to 0. Okay, so I fill in the right side of the equation. I know the mass is 3. I don't know ax, so I leave that in as an unknown. And then I go on to fnet, or the y stuff. Okay, again, I'm still on step 2, determine if the object is accelerating. I look at the y forces. Is the object accelerating based on the free body diagram? No, at least not in the y direction, because if I have 45 newtons up and I have 45 newtons down, that means the net force in the y direction is 0. That means there's not going to be any acceleration in the y direction. And that doesn't necessarily mean that the object is not moving in the y direction, but I know there's no acceleration, which means that this entire side of this equation is going to be 0, because I have the mass is 3. If there's no acceleration, that means ay is 0. That means this entire right side of the equation will be 0. Okay, so that is step 2. Step 3 says to write down the sum of the forces before you plug in numbers. Now here, for some reason, they're all labeled as F, and so that's kind of difficult to do, but just to clear this up, let's call this one F1, F2, F3, and F4, just so you can see what the sum of the forces would look like. So in the x direction, I would have F1 plus F2. In the y direction, I would have F3 plus F4. And if you're wondering, like, why is he writing out the sum of the forces if he already has the numbers? Because in a lot of problems that you're going to be doing, you don't have the numbers given to you. These are very basic examples we're doing. Okay, there's a lot of problems where you're actually trying to find one of these unknown forces. And so you have to write out the sum of the forces without any numbers, just so you can kind of see where your unknown is in the equation. Okay, so that's why we're doing this. Now that I've written out the sum of the forces, I'm done with the third step. Now I can just plug in numbers and solve. So F1, I'm going to put 15 newtons, plus F2, I'm going to put negative 45 newtons. Make sure you remember you're adding vectors and the direction matters. This is 45 newtons to the left, so that's why it's negative 45 right there. And then for the y forces, I'm putting 45 plus negative 45 equals 0. Okay, so my overall result is basically that all the forces cancel out in the y direction. That means ay is 0. Ax, on the other hand, if I simplify this, 15 and negative 45 give negative 30, and that's equal to 3 times ax. So ax is equal to negative 10 meters per second squared, and ay is 0 meters per second squared. So this object is not accelerating in the y direction, but it is accelerating in the x direction. Specifically, it is accelerating at 10 meters per second squared to the left. Okay, I say to the left because this negative sign here is in the negative x direction. Okay, so here is the acceleration of this object. That is example 1.5. Okay, so pause there if you need to look at that some more. Okay, so hopefully you're getting a little used to the process solving second law problems. Before we do any more second law problems, there's something else I want to talk about. So there's not a ton of equations in this unit, but one of the equations we're going to be working with a lot is the equation for the force of gravity. Okay, this is one of the only equations, this is one of the only forces that actually has an equation associated with it. There's a lot of forces that there's not an equation to directly solve for that force, but Fg, there is an equation for Fg. Okay, so here it is. Close to the surface of a planet, and I say this because you need to understand anytime you're dealing with an equation, you have to understand the limitations of that equation. Okay, so for example, constant acceleration equations can only be used if you have constant acceleration. So this part I just underlined, this is the condition for the equation I'm about to write. As long as you are relatively close to the surface of a planet, the force of gravity, aka the weight, remember force of gravity and weight are the same thing, the force of gravity acting on an object is equal to the product of the object's mass and its acceleration due to gravity, which is g. Now remember that on Earth, the value for g is approximately equal to negative 9.81 meters per second squared, which we typically round to negative 10 meters per second squared, at least in the simplified calculations. Okay, although you do need to understand that if you were on a different planet, you would have to use the acceleration due to gravity value for that planet. So this is one of the only equations that you'll see in this unit. Okay, so this lets you calculate the force of gravity acting on an object. Okay, so pause there, make sure you add that to your notes. And then we'll just do a few quick examples. Okay, example 2. A box with a mass of 20 kilograms sits at rest on a table. Draw an FBD and calculate the magnitude of the normal force acting on the box. Now, at this point, if you're not paying attention and you don't understand that solving second law problems, you should always follow the same steps, your first question is probably going to be, what is the equation for normal force? Well, there's not one. Okay, there's no way to solve for normal force without using Newton's second law, either implicitly or explicitly. Okay, there is not an equation for normal force. So this is a second law problem. So, like any second law problem, you always start with a free body diagram. So, this is a simple one. We have a box on a table. We have force of gravity going down. And then because it's touching a surface, we have a normal force which is perpendicular to the surface, which in this case is going to be directed up, like this. And it's at rest, and so we draw this FBD so that these two forces cancel each other out. Make sure you don't confuse Fn, which is normal force, that's the force from a surface, with Fnet, which is net force, completely different. Okay, so step 1, done. Step 2, write out, or determine whether or not the object is accelerating. Notice I'm writing Fnet y because the only two forces I have are in the y direction. Is this object accelerating? No. How do I know that? Well, it says the box is at rest, which means it's not moving. If it's not moving, if it's staying at rest, it's not accelerating. That automatically makes the right side of this equation equal to 0. Now I go to step 3. I write out the sum of the forces. Okay, remember what I said. Always write out the sum of the forces before you plug in numbers. This is why. All of a sudden, I have an equation that has Fn in it. That means as long as I know what Fg is, I can easily find Fn. Luckily, I don't have an equation for normal force, but I do have an equation for Fg. Fg is equal to mg And so if the box has a mass of 20 kilograms, and it doesn't say, but let's assume this situation takes place on Earth, the acceleration due to gravity on Earth, let's say, is negative 10 meters per second squared. That means Fg, the weight of the box, is going to be negative 200 newtons. Okay, so the force of gravity on the box is negative 200 newtons, and now I can plug in and solve. Fn plus negative 200 equals 0. Fn equals 200 newtons. And we're done. Okay, another simple calculation problem involving Newton's second law. And this is exactly what your work should look like for these problems. Alright, pause there if you need to look at that some more. Okay, let's take a look at one more quick calculation example, and then we will stop it there. And this one really is not a second law problem, but example 3 says a rock on Earth has a weight of 15 newtons. First question says calculate the mass of this rock on the moon. Okay, so let's think about this for a second, because this is kind of a concept question. We know that the force of gravity equation is Fg equals mg. Now, somebody might say, wait, shouldn't the force of gravity be negative? Yes, it should be, but in normal conversation, people don't talk like that. Okay, people don't go around saying, you know, I weigh negative 100 pounds. Okay, that doesn't happen. So you need to understand when they say this rock has a weight of 15 newtons, they're talking about the magnitude of the weight. When you go to plug in for calculation purposes, what you're putting for Fg is not 15, but you would actually put in negative 15 because you're smart enough to take into account the direction. Okay, so when you have problems saying things like, you know, it weighs 15 newtons, you need to be smart enough to understand they're only talking about the magnitude, just the number part. The actual force of gravity would be 15 newtons down, and so you would put that negative sign to indicate the direction is down. Now, I don't know the mass of the rock on Earth, but I do know the acceleration due to gravity on Earth is about negative 10. And so I can very easily find the mass of the rock on Earth is 1.5 kilograms. But wait, you say, the problem doesn't say to find the mass of the rock on the Earth, it says to find the mass of the rock on the moon. Okay, this is kind of a concept question where you have to recognize it's the same thing. Okay, mass doesn't change from the moon to the Earth because mass is a measure of inertia. That just has to do with how much matter makes up the object. Okay, so it's 1.5 kilograms on Earth, it's still 1.5 kilograms on the moon. Okay, so that's the answer to the first question. Now the second question says the weight of this rock on the moon where the acceleration due to gravity has a magnitude of 1.63 meters per second squared. So now we're asked to find the weight, which is force of gravity. We know the equation for force of gravity. And now we know the mass is 1.5 kilograms. G, the acceleration due to gravity, has a magnitude of 1.63 meters per second squared. So what am I going to plug into this equation? I'm going to put negative 1.63 meters per second squared. Why am I putting negative? Because the direction of the acceleration due to gravity is down. Okay, so the magnitude might be 1.63, but if the direction is down, I indicate that with a negative sign. Okay, so I plug this into my calculator to calculate the force of gravity for the moon, and I do 1.5 times 1.63, or negative 1.63, and I get Fg equals negative 4.5 newtons. Okay, so compare that to the 15 newtons it weighs on Earth, and you'll see it's actually quite a bit lighter on the moon, just because the acceleration due to gravity on the moon is so much less. So that has nothing to do with Newton's second law, but just getting more comfortable with the force of gravity equation, since we'll be using that a lot over the next couple months. Okay, we're going to stop it there. In the next video, or the next thing for us to talk about is elevator problems, but I might talk about those in class. As always, please let me know if you have any questions, and I'll see you guys in the next video.